You should recognize this as the formula for converting between Fahrenheit degrees and Celsius degrees. But what if instead of solving for Celsius, I wanted to give you Celsius and solve for Fahrenheit? Well, one of the things we can do is we can rewrite this equation to solve for F, so that it says F equals instead, and that makes the equation more usable for us if we know the degrees Celsius. Now, in order to solve this equation for F, the first thing we'll do is get rid of the 5/9. Since this is 5/9 times F minus 32, to get rid of the 5/9, we're going to multiply the other side by the reciprocal of 5/9, which is 9/5. Oops. So 9/5 C equals F minus 32. And then all I have to do is add 32 to the other side. And it turns out that this is the equation for finding Fahrenheit degrees when you know Celsius. Well, what we've just found is something called an inverse function. In Algebra 2, we studied inverse functions. Inverse functions were pretty easy. So let's start with something very basic. First, we would be given like a table of values. Just random, I'm just picking whatever numbers. And we would ask you to determine the inverse of this set of data. The way an inverse worked is you would take the ordered pairs and you would flip them. That was all we did. It was pretty easy. Well, then after we took our ordered pairs and we flipped them, then we gave you a simple graph. So for example, y equals x squared. The graph of y equals x squared goes through 0, 0, 1, 1, 2, 4, 3, 9. It also goes through negative 1, 1, negative 2, 4, and negative 3, 9. If I knew some of the ordered pairs that lie on the graph, I'll put them in table format. Negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. We would have you graph the inverse by simply switching the ordered pairs. So instead we're going to graph 9, negative 3, 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2, and 9, 3. And this is what the graph of the inverse would look like. After we graphed the inverse, we mentioned that an inverse is actually a reflection over the line y equals x. Remember, we talked about symmetry over the x-axis, the y-axis, the origin. One of the symmetries we talked about was symmetry over the line y equals x. If this were a sheet of paper and you were to fold the paper on the dashed line, the black parabola would lie on top of the red parabola. But what if I wanted to find the equation of the inverse? Well, the way it works is I would take the original equation, which was y equals x squared, and we flipped x and y. The reason we flipped x and y was because that's our symmetry over the line y equals x. And then we're going to solve it for y. In order to solve it for y, I need to take the square root of both sides, because to get rid of a square, you do square root. It's just that when I take the square root, I'm going to instead put plus or minus in front of the square root of x. If you don't put plus or minus, and you were to graph it in the calculator, you would only see this top half of the graph, because that's y equals positive square root of x. The bottom half of the graph is y equals negative square root of x. And that's kind of one of our limitations with the graphing calculator, that in order to see the entirety of the graph of the inverse, we would have to graph two separate pieces of that function. I shouldn't call it a function because that's not a function. So because that sideways parabola is not really a function, let's talk about determining if something is a function and if its inverse is a function. This is the absolute value function that's been shifted up 1 unit. So it's a v that's been shifted up 1 unit. If I graph that, it would go through 0, 1, it would go through 1, 2, it would go through 2, 3, it would go through negative 1, 2, and it would go through negative 2, 3. All right, there is my v. And it's a function. And the reason it's a function is because if you remember from Algebra 1 and Algebra 2, something called the vertical line test. If you take a vertical line anywhere on that v, the vertical line will never touch the graph in more than one location. Well, now let's look at the inverse. So if the original graph has 0, 1, then the inverse must have 1, 0. If the original graph has 1, 2, the inverse must have 2, 1. If the original graph has 2, 3, then the new function has 3, 2. If the original function had negative 1, 2, then there would be a point at 2, negative 1. And the original graph had negative 2, 3, so the new function has 3, negative 2. And remember, I said this is going to be a reflection over the line y equals x. So if it looks like a reflection over the line y equals x, we probably graphed it right. But the question is that red graph a function? And the answer is no, because if you perform the vertical line test, that red vertical line will touch my v in 2 places, not 1. It's not a function. But the book also mentions something called a horizontal line test. The horizontal line test, if you perform it on the original graph, the black one, notice that the horizontal line hits the graph in 2 locations. That means that the graph of its inverse is not a function. But it doesn't matter if it's a function or not because the red graph is still called a relation. Also in Algebra 2, we introduced you to this notation. This is the notation we use for the inverse function. It's pronounced f inverse of x. I know it looks like it says f raised to the negative first power, and it's not. We pronounce it f inverse of x. In order to find the equation of an inverse, you would flip x and y, and then solve that new equation for y. So I'm going to subtract 2, and then I'm going to divide by negative 3. And then this would be the equation of the inverse. Notice that the original graph was a line, so is the inverse. Let's try that again. I want to find the equation of the inverse of f of x is equal to 1 over x cubed. So I'm going to flip x and y, and then I'm going to solve this for y. Now, I want you to notice this is a proportion. So in order to solve it, I'm going to cross multiply, and then I'm going to divide by x. And then in order to get rid of a cube, you would cube root the other side. That is the equation of the inverse. Now, in these previous examples, when we wanted to find the equation of the inverse, we switched x and y and solved the new equation for y. In real-world formulas, though, where we do actually find equations of inverses to help us, we don't actually switch the input and output. So in this last example, if you deposit $1,000 in a savings account with an interest rate of R compounded annually, then the balance in the account after 3 years is given by the function B of R equals 1,000, 1 plus R to the third power, where R is written as a decimal. Find a formula for the interest rate R required to achieve a balance B in the account after 3 years. In other words, they want us to solve this equation for R. So the way the original equation is set up, I would give you the interest rate, you would plug it into the equation, and then you would solve for the balance B. But what if I want to find a particular balance? So I need to find the rate. So even though I'm not switching the input and output, I am still finding an inverse by solving this equation for R. To solve it for R, the first thing I would do is divide by 1,000. The reason I'm dividing by 1,000 first is because it says 1,000 times the quantity 1 plus R cubed. Next, I have to get rid of the cube before I can move that 1. So to get rid of a cube, you have to cube root the other side. And notice the entire fraction is under the cube root. Then I can subtract 1. So if I know the balance, but I want to find the interest rate, I would do the cubed root of the balance divided by 1,000 and then subtract 1 from that answer. So now that I have this equation, what interest rate will yield a balance of $1,100 after 3 years? So I'm going to plug in 1,100 for B. And then I'm going to simplify this. I get, let's see, whatever the cubed root of 11 over 10 is. And I'm going to subtract 1. And I'm going to get R equals 0.0323. Remember, the rates is a decimal. So if I want to turn that back into a percent, because normally interest rates are given as percents, you would multiply that by 100 and find out it's approximately 3.23%. I want to give you one last real-world application of finding an inverse. We know from geometry that the formula for finding the area of a circle is A equals pi r squared. A lot of times we write that as a function, so instead of A, we say A of R. The reason it would be written as a function is because R is the number that tends to get plugged in. You normally know the radius, you're going to plug it in and find the area. But what if I knew the area and I wanted to find the radius? Well, I would solve this for R. In order to solve it for R, first I would have to divide by pi. And then to get rid of the square, I would square root the other side. And this would be the equation of the inverse if I knew the area and I wanted to find the radius. Now, unlike a previous problem, when I take the square root here, I'm not going to write plus or minus. And a problem towards the beginning of the video, I did put plus or minus. Let me ask you this question. Can you have a negative radius? I think not. And so that's why I don't use it. And that is inverse functions and relations.